Okay. And my apologies, everybody. This is not going as smoothly as I would have hoped, but we'll still get through it because what's really important is the stuff that we're learning, right?
It
So
wouldn't be ham radio
if it were
if
perfect,
it were perfect.
that's right.
Yeah, the one thing that would be nice that was brought to my attention is when you're going into this, give us a little bit of an idea about what you're going to go into, because you kind of jumped in with both feet there for a second.
I did. And part of that I think was the fact that I got a little screwed up by this whole no whiteboard thing. So my apologies. That was a little abrupt.
That was a good comment, though. I kind of gathered right before the break the whole purpose, and this is not entirely, not the whole, but a big piece of it was to know, understanding wavelength frequency, all of that is to know your antenna.
Yeah. Well, it's a physical understanding of space. It's all the stuff that you can learn from all the stuff that we can learn from, all the physics classes you take, except most of the studies are done with light. If you teach physics, you've heard of something called a Michelson interferometer experiment, and doing, single slit, double slit experiments, things like that. Well, but those are done with light, which is great because you can look at it under a microscope. You can see it, on a piece of paper, but it's very hard to relate that to something physical that you can actually see other than like a diffraction grating. I was explaining to somebody the other day that, okay, here's a handheld. Now take it and move, just walk around the room, and you will notice that this handheld radio goes from being, you'll hear everybody perfectly, and then you'll hear nobody. And then you'll hear everyone perfectly again. And then you'll hear nobody. So the question is, why is that happening? And the answer is that it's happening because you're moving around from place to place. And as you move around from place to place, you have areas of constructive and destructive interference. And those are really defined the same way that you would see light, you'd see like a diffraction grating or something like that. Except that you're actually hearing it because it's physical, it's big. Because the wavelengths are much, much longer. So
we've got a bunch of guys here in Phoenix that are on GMRS that use handhelds, and they'll be sitting in their house on their couch and can't understand when they get up to go to the kitchen why they can't hear us.
Yeah, exactly. So yeah, exactly. Let me just look at account management. Okay, so I'm not going to get this to work right now, but I will get it to work eventually. Okay, I'm getting closer. Everybody ready to move on to the next thing? And again, my apologies I really did try it out beforehand, and it was working. So we're going to show a new whiteboard, which I really hate. And I don't know why it's not, see, hola, ciao. I don't know why it's not letting me use the old one if I want to. So everyone clear your cursors away from there so we can do this. And we will get this figured out. And okay, here we go. So now we are now into the place where we are drawing things. And okay, so we said the last thing before break was that here's our piece of wire right here. And our piece of wire is such that it's a piece of wire, right? Now, does everyone know what wire is made out of? What's wire made out of? Metal, usually copper because it's pretty conductive and it's relatively cheap. And if anybody wants to follow along where we are, I would say that more or less we're getting into like page 5 of the book. So page 5 of the book is electrical principles. But really what we're going to deal with first is kind of like physics. So here's an atom, there's a proton, and there's a neutron. And we're going to have a bunch more of these in the nucleus. And that makes kind of like a big ball of stuff all held together by the strong force. And then spinning around that, and there's also the weak force in there. But then we also have these electrons, which are kind of like floating around in these clouds based on probability. But there's a match in the number of electrons and protons in this atom. It's a stable atom. If we put 29 of them together, 29 electrons and 29 protons, we would have copper, because copper has an atomic number of 29. Or is it 27? It is 29, right? Yeah, because silver is 47. So basically what we end up with copper is that we have, in each one of these atoms, we have electrons. And the way that the copper atom is built, you can actually push an electron into the area of a copper atom, and an electron will pop out the other side, kind of evening the balance. Well, if we do that enough times, we push electrons into here, and what comes out the other end, everyone? And this is where we get really interactive. So, okay, so an electron goes in, electron comes out the other side. So as that happens, we have an electron that goes in, an electron that goes out to match it. So this is a piece of copper. It does not have the ability to store extra electrons. Therefore, if one goes in one side, one goes out the other side. An electron is a fundamental particle which has a charge of negative. So an electron is a negatively charged particle. Can't get any smaller than an electron. And so the reason we call it electricity is because it's the flow of electrons. So now what we're going to do is say, if we could measure the number of electrons that flow in and therefore out every second, this is known as a current. That is known as our current. That is measured in amperes, named after ampere, and it is given the big letter I. That is the symbol for our current. So if you see either an A or an I, we have our current, which is letter I, measured in amperes, which is letter A. Now, as it turns out, an ampere is a lot of electrons every second. Like a lot, like 10 to the 19th electrons, because electrons are really, really tiny. So an ampere is actually 1 coulomb of electrons every second. It's a lot of electrons. But what we do is we kind of normalize this and say our unit is 1 ampere. Now, we can have, that's actually a pretty good unit, because we could have a current flow of 3 amperes. This is not an overly large current. We could also have a current flow of 0.001 amperes. That's not a particularly small current. It's a small current, but it's still a viable number. So when we start looking at bigger things, we could have a flow of 3,000 amperes. So to make room for these things and get rid of all those decimal points, we say, okay, well, I'm going to replace a certain number of zeros or a certain number of decimal points with a letter. So I'm going to take this 1,000 and I'm going to write in the letter kilo. If anyone's ever heard of a kilometer or a kilogram, kilo means 1,000. If something is 0.001, I'm going to replace that with a little letter M for milli. So that would be 1 milliampere. This would be 3 kiloamps. I could also, if I look at my charts and say that I have a million of something, million is replaced by this big letter M. What does that stand for?
Mega.
That stands for mega. That means million. Now, I could write out 1 million, 1 0 0 0 0 0 0. Somebody count the number of zeros for me. What do we have?
6.
That's 6. Does anybody disagree that a million is equal to 10 times 10? And I'm not going to write it all the times. 6 times?
Agreed.
Agreed. Okay, so that translates to, by notation, scientific notation, 10 to the 6th power. It's 10 times itself 6 times. Now, I could also do 0.000001. Now, this is 1/10 times itself 6 times, which would be 1/10 to the 6th power, which is equal to, by convention, 10 to the minus 6th power. So if I were to do that, that would be replaced by this little letter mu, which means micro, which means 10 to the minus 6th. So this is how we do our placeholders. This is how we get rid of all those annoying zeros that we would otherwise have to maintain. And the interesting thing about that, can anybody see the second page, or are you still looking at this one? I'm assuming we're still looking at the same one. Okay. So what we now have here, oh, I can scroll. Look at that. But you can't see it. Wow. That's annoying. Okay.
I think if we scroll, we can see it.
Yeah, if you scroll, you can see it. But I really need to work on this.
Yeah, we have the capability of scrolling our own page.
Yeah, okay. Yeah, I don't particularly like that.
But we need people to remove their cursors off the page. Though,
Yes. Yes, everybody keep your cursors off the page. We will get this worked out, I promise. I know I found the setting, I just haven't got it yet. Okay, so now we have our units, which are bigger and smaller. We have our milli and our micro. Here's our milli, here's our micro, and then here's our kilo, and here's our mega, which is getting bigger. Then we could go to little n for nano and little p for pico. And getting bigger, we can go with other things. You may have heard, like, you have a gigabit network, or your hard drive is a certain number of gigabytes. And then we go to tera, and we can go bigger and smaller even than that. And all those really do is they just replace our zeros. So let's say I had something that was 3 pico amp. I could write that out and say, okay, this is 3, 6, 9, 12. I could write that out by saying this is 0.0 and write 11 zeros with a 3. The question that I have is, does that really mean anything to anyone to see all those zeros, other than to know, wow, that's really small? What that really does is that it means that you're probably going to end up leaving a 0 out when you copy it down. So we would normally write this as 3 times 10 to the minus 12th power in scientific notation. And that minus 12th power is very convenient, because let's say we were multiplying this by something that is 1 times 10 to the 12th power. Well, okay, 3, 6, 9, 12. That would be a tera something. But if we have this times that, the 3 times 1 is just 3, and 10 to the minus 12th times 10 to the 12th power, you add the exponents together, and you get 3 times 10 to the 0, which is 1, and that's just 3. So that is the power of being able to use our exponents and use our shorthand. And because electrical things often deal with very, very small and very, very big values, that's where we start to work with that. Okay, so now we're going to go back to our ridiculous whiteboard until I get the old whiteboard working. Keep saying add a sticky note. I don't want to add a sticky. Okay, so now we're going to have our little electron with a minus sign because it's a negatively charged particle. And we're going to have a piece of wire and we're going to dump our electron into here, and that's going to come out here. The number of things, the number of coulombs of electrons that we get flowing through every second is known as our current, and that's measured in amps. The amount of push that we have that pushes electrons into these things, this is known as the voltage. Voltage has another name, EMF, which is electromotive force. Basically, literally, electromotive, electrons, motive, movement, and force. Force is the amount of push. So it stands to reason that the higher the voltage or EMF or electromotive force there is, the greater the ability of whatever this is out here to shove electrons into and through this thing, whatever that thing is. That could be a piece of wire. That could be a block of glass. That could be salt water. That could be any number of different things. So we have a voltage which pushes electrons. The higher the voltage, the greater the ability to push. That generates a current, which is our letter I, which is measured in amps. And it is proportional to the intrinsic property of this thing. This has a value of R, which is resistance. We measure it in ohms. That is named after Georg Simon Ohm, who was a scientist in the 1800s as well. Notice we have volts named after volta, amps named after ampere, and ohms named after Georg Simon Ohm. So again, that is an intrinsic property of the material that is being used as a conduit for our electrons. So let's take a look at our piece of something that we're using.
So Scott,
yes.
That would mean that aluminum or copper or gold might have a different type of resistance.
Oh yeah, they do. They definitely do. And let's take a look at just a block of something. Right? So this is a material. We're just going to say it's a material. We don't know exactly what it is, but we're going to have a voltage over here, and it's going to generate a current that flows through it. Okay? By Ohm's law, V, or we can actually use in substitution letter E for electromotive force, is equal to I, which is the current, times R, which is the resistance. This is Ohm's law. E equals I times R. Now, I will tell you that even with an engineering degree, when you actually go into the real world and you start to solve problems, E equals I times R, you can draw that circle the same way. You take the one that you don't know and you cross it out, and then you have a divider right here. So R is equal to E divided by I. You can do the same thing if you don't know the voltage, that you have E equals I times R. This becomes a multiplication bar, a multiplication line right there. So all you have to do is be able to, if you can't remember how to rearrange your formula, all you have to do is take your, all you have to do is be able to draw your circle, E equals I times R. There are 3 circles that we're going to be using in this class. One of them we already saw, which was the 300. lambda, and F.
And it's worth noting that this is test material right here.
This is test material. That's right. And this is your foundational stuff. The other one that we're going to do is P equals I times E. Once you get your piece of paper, if you want, you start with a blank piece of paper. You draw those 3 circles. That solves pretty much all your math. Okay. And I don't know how to get people's things off the screen. I really don't. And I'm sorry about that. It looks like a bunch of buzzing bees.
Hey,
yeah,
Scott,
yeah.
just go to those 3 lines, remember? Go to those 3 lines, then view and uncheck collaborator cursors.
They are unchecked.
Yeah, everybody has to do it themselves, and everybody
my
has to keep
God.
their cursor off the screen.
Oh my God. I can't wait to disable this thing.
If
All
everybody
right.
just moved their cursor all the way to the right, then it wouldn't be on the whiteboard.
Yeah. And again, my apologies. I love Zoom, but you know, and I know it's probably an improvement, right? We'll say it's an improvement. It's just an improvement I didn't ask for. Okay, so anyway, we have our V, we have our V or E, and we have our I, and we have our resistance of our material. And again, that's measured in ohms. So if you want to think of this as like a creek bed, right? And you take a bucket of water and you pour it in on the left-hand side, how much current is going to flow? Well, there's a couple of things that can have some impact on that. The first one is, what is the slope of the river? The second one is, how narrow is the creek bed, or how wide is the creek bed as the water flows from left to right? So that will basically determine how fast the material flows from left to right. Did I do that, Zoom, or did somebody else? Geez, I didn't even know I could do that. Wow. My apologies for being completely clueless on this, everyone.
Bottom right hand, you see the 2 magnifying glasses. You can plus or minus your screens, and it'll enlarge it or decrease it.
Okay, but can I grab it and move it?
You can scroll through the whiteboard if you move the whiteboard with yourself.
Yeah, but how? Oh, there we go. I got to grab it. I got to grab the curve.
Yeah.
Nope, that's not it either.
If you got a touch screen, you can use your finger to move the whiteboard around.
I don't. This sucks. Well, anyway.
Yeah, you can also left click on the mouse anywhere on the screen and grab it and pull it and move it wherever you want.
I tried that. There we go. It's a right click. Okay. Right click is the grab. Okay. All right. So anyway, here's our resistance, the letter R. So now things that can alter the resistance, you can have a different material. You can have it being wider. You can have it being narrower. You can also have it being longer. So resistance is a function of the material that it's made of, as well as the cross-sectional area of the material, as well as its length. So if something is longer, it's going to have a higher resistance to flow. If it's narrower, it's going to have a higher resistance to flow. Okay, so very simply now, what we're going to do is going to get rid of this. I mean, I like learning on the fly, but not in front of 60 people.
So if you were wiring a house and you wanted a 20 amp circuit, you'd use what, like a 12 gauge wire?
We're getting to that.
Okay.
We're getting to that. Okay. So now what we're going to do is E is equal to I times R, and we're going to make a simple circuit. Circuit, where comes from the word circle. We're going to have a battery right here. We're going to have a battery which has an electromotive force, which is a voltage, which is the ability to push electrons. Now, what charge did we say that electrons have? Are they plus or minus, everyone?
Minus.
They're minus. That's right. Okay. But notice which direction the current is flowing in this circuit. Does it flow from plus to minus or minus to plus?
Minus to plus.
Well, yes, you would think so, but which way did I draw it?
Plus to minus.
Plus to minus. And that's because there was a mistake made before people knew what electrons really were. And in fact, electrons really do flow in this direction, drawn by hopefully the red. Nope, not red. Let's make it red. Drawn by the red pen. The electrons, because they're negatively charged, flow out of the negative terminal up to the positive terminal. But in effect, because people didn't know what electrons were in the 1850s, they just knew that there was something. They assumed, okay, well, things must flow from the positive terminal to the negative terminal. And it's 170 years later. And because everybody already knows, obviously, that electrons flow from the plus to the minus, that is the convention that we all have to live with. As an engineer, or if you're into physics, it is painful to understand that. It is, you just have to accept the fact that mistakes were made and we're still living with them today. So what we're going to say is that we have an electromotive force of 10 volts over here and a resistor of 10 ohms. That is a lumped value. It's all in one little blob. We're going to assume that our wire has a resistance of 0 ohms. If something has a resistance of 0 ohms, what does that make it?
Superconductor?
That makes it a perfect conductor, yes. If something has a resistance of infinity ohms, what does that make it?
Wood.
Well, it's not wood. You can push current through wood.
Insulator.
Yeah.
Insulator.
Glass.
If it's well, you can push current through glass.
Non-conductive.
Yes, it makes it non-conductive if it's basically that's known as an open circuit where you can't push something through. But for the sake of this, we're going to draw this as a closed circuit. 0 ohms is also known as a short circuit. So this is a perfect wire with 0 ohms resistance. Okay, so now what we're going to say is, as we do this, we have 10 volts and 10 ohms. E equals I times R. And we're going to look at this circle over here on the left. And which one don't we know? We don't know the current, so we're going to cross that out. And then we have I equals E divided by R, which is 10 over 10, which is 1. Okay, that just did it again. Why? Okay, Heather, you don't see the current chalkboard. You're going to have to drag it into the area that you can see it.
Now that you just did what you did when it moved it,
Yeah.
I lost my ability to drag.
I see a scroll bar at the bottom of the.
Yeah, you're just gonna have to go right click on it now, because mine was left click and now it's right click.
What the heck?
Yeah, that worked.
And somebody just moved my number 3.
We have to also keep in mind that some of us, not all of us, are on a computer.
Yeah.
Like I'm on a computer. Some of you guys are on phones. Some of you guys are on iPads. It's going to be different for every one of us.
Oh my God. Okay, well, I want to send Zoom a big single finger thank you note after this for changing this. Sorry, I'm not going to say which finger it is. We will get better at this. I'm gonna eliminate this thing and go back to the original. And someday this may be useful, but it is not today. So
I can take a stab at which finger it is, and I imagine it's not the pointer and it's not the
not
ring,
my
but it's in the
thumb.
middle.
It's not my thumb. I'm not giving him a thumbs up.
It's okay. You're not
The little
broadcasting
finger.
over with the FCC listening.
Yeah. Okay. So that means that our current is 1 amp. So in this little circuit, which is mostly undrawn, which I'm going to redraw. There we go. Our current is now 1 amp. So that means that if I know 2 of my 3 values, I know the third one too. So this is the basis for all of the basic electrical stuff that you're going to be doing on this exam. The other thing you're going to be doing on this exam is
Okay, question for you real quick.
Yeah.
Okay, when you put on there, you put it at 30 volts, but then when you put it down into where you're figuring out, you put it at 10.
I thought I put 10. Let me redraw it.
Okay. And so that's what confused me a little bit, because I started writing it as 30 and I can figure it out.
Yeah, I thought
you had it at 10, but when you are over here, right here, you
Yeah.
had this originally at 30.
Oh, okay. Well,
and so that was, yeah.
Okay,
so that's
sorry. I thought
that's
I
what
had
kind of
10.
confused me when I saw 10 divided by 10 over here, thinking, where do you get the 10
Yeah.
when it was supposed to have been 30 as far as I was looking at?
Okay.
So I just wanted to point that out.
Okay.
I understood now what you're doing, but I just wanted to point it out because others might have been confused with it.
Okay. All right. So now moving on, we have our circuit again. Now we've determined that, again, we don't know the current. We can cross that out. I equals E over R equals 10 over 10 is 1 amp. So we can put 1 amp right here. So now the question becomes, we have another equation. What are we going to do with that equation? And that equation is P-I-E. This is easy to remember. It spells the letter pi, it spells the word pi. And this is a relationship between current and voltage. And notice this big letter P, this is power. And that's measured in watts, named after James Watt, who was a Scottish scientist who studied power and worked on steam engines and all kinds of cool stuff like that. And what's nice about power is that power is a unit of dissipation of energy. Energy is measured in joules per unit time. A watt is a joule per second. And what's great about power is that it does not matter what form that power and what form that energy take. So that could be potential energy. That could be, when I say potential energy, okay, so let's say I'm on a cliff and I'm the coyote and I'm wanting to drop a boulder on the roadrunner. So here's a boulder, right? That boulder has potential energy. And it's energy that's been done. It's been brought up to the top of the cliff by doing work against gravity. That is still energy. If I drop that and there's a certain amount, it dissipated over a certain amount of time, it has a certain amount of power that it is dissipating over a period of time. Now, I could also take this energy as let's say, roll it down here, and let's say I put a ramp at the bottom. That energy, which was potential up here, is now changed into kinetic energy, which is energy. Man, it's rough. I'm just going to put KE. So that potential energy is now changed into kinetic energy. The other thing that I could do is, let's say that instead of turning it into kinetic energy, I could just actually put like something down here that would absorb the energy of the velocity as it was falling, and could do something like spin up an electric motor. That electric motor is connected to a battery or something to that effect. And I could use that energy, which was potential energy against gravity, to charge up this battery. So energy, due to the conservation of energy, can neither be created nor destroyed. It just changes form. What that means is that the energy that we have stored in our battery, is the same energy that will come out over here in our resistor. So if it, as let's say that we are putting energy into the system from the battery and it comes out in the resistor, we have electrically stored energy in the battery. How does it come out in the resistor? What do you think?
Amps.
Nope. Energy can neither be created nor destroyed. It just changes form.
Yep, it's being
Current.
converted into
Current.
heat or
Being
light.
converted into heat or light or both. That's right. And if anybody has ever accidentally burned up a resistor, what happens to it? It turns black. Sometimes, if it gets hot enough, it will actually start to glow a little bit before it turns black and then becomes a little carbon crisp and makes a lot of heat. So energy is neither created nor destroyed. It just changes form. So we can actually look and see how much energy is being dissipated per unit time by our power equation, which is the other half of Ohm's law. P is equal to I times E. So as that happens, we have, in this case, we don't know our power, but we can calculate it. Cross that out. P is equal to I times E. And in this case, we have current, which is 1 amp, times 10 volts is 10 watts. So a watt is a joule per second. That means that we are supplying energy from the battery at a rate of 10 joules per second, and we are burning it up in this resistor at the exact same rate of 10 joules per second, or 10 watts. So interestingly, if this is a resistor and it looks like this, which is how most resistors look, just a piece of carbon with a couple of markings on it, like little stripes, indicating how big the resistor is. It also has a rating that might say 1 watt. So if I have a resistor that has a power dissipation capability of 1 watt, and my calculation just said that the power that we're going to be dissipating 10 watts in that resistor, what will happen to my resistor?
Does it catch fire?
It can catch fire. I've seen that happen. If you're lucky, it will just turn white hot or red hot, then turn a little bit white, and you'll see a flash, and it will just end up in a puff of smoke. Typically, that is not the result we want, correct? That's usually you usually think of that as a bad thing. Okay, so we have the ability to do something about that by adding another device that, okay, well, we could always make the resistor bigger, right? But let's say that we don't have the ability to do so. Well, let's say that we want our maximum power to be 1 watt. So how do we do this? We go through our power calculation, but this time we can't change our battery. And what we want to do is say that we want a maximum power of 1 watt. We know we're at 10 volts. The question is, how much current can we allow? Well, okay. Well, we know our power. We're going to say this is 1 watt because our resistor can only take 1 watt. And we don't know our current. So I is equal to P divided by E is equal to 1/10. 1/10 of a watt. Or sorry, 1/10 of an amp. So that means that we have to somehow limit our current to 1/10 of an amp. So clearly this resistor is not the proper value anymore. So now we can go back to Ohm's law and we have our E is equal to I times R. Now we don't know what our resistor value is. It's a new value. And E divided by I is equal to 10 divided by 1/10. What's 10 divided by 1/10? We're now at 100 ohms. So in order to do that, we would now say that we have a resistor of 100 ohms. And that would basically say that we are now able to dissipate the proper amount of heat. Now, it might not be exactly what we want, but for now, that's okay. So we this is how you creatively use Ohm's law to figure out what things need to be. Now, we also have, let's say this resistor is here and something happens, and instead of this resistor, we end up with a heater and it develops a short circuit or a partial short circuit, so that instead of that particular resistance of 100 ohms, it's now 10 ohms again. Well, from our first calculation, we said that's going to be 1 amp. So if this wire is designed to handle 1/10 of an amp, what's going to happen to the wire suddenly when it's carrying 10 times as much current as it's been designed to?
Heat up.
It's going to heat up. And what will that do eventually? You have
Melt.
you have two options. Number one, the copper melts. Bad, right? What's number two? The copper doesn't melt. And what does it do? It just keeps getting
Overheats the system.
It overheats the system because the copper wire is inside insulation, which is inside your wall. And what happens to it then? Or it's under a carpet. It sets the carpet on fire.
Yeah, call the fire department.
And you call the fire department because it burns your house down. So we add a device in here which has a current limiting effect. This is known as a fuse. A fuse is designed to melt intentionally on purpose at a certain current, so that when Ohm's law says that if a certain amount of current is flowing through there, this begins to melt. Once it melts, what does it become?
Breaks the circuit.
It breaks
Open
the circuit,
circuit.
and you no longer have a closed circuit, and the situation is averted. Now, the thing that you built doesn't work anymore, but at least you didn't burn your house down. And this is a fuse. A fuse is designed to prevent overcurrent and prevent overloading of system. So why would you never, if you didn't design a system, replace a fuse with a different one? If you
Maybe
weren't
the
the one
wire's
who
not
designed
designed
it.
for it.
That's right. Okay, so now the question is, somebody asked, let's say that this is your house wiring. What would be from your breaker to your outer, to your receptacle, which looks like this? There's your power receptacle. And you have 3 wires. The green one is the ground. Ground is safety. The hot one is black, and the neutral, which is the return path, is gray. If you are building a circuit that is supposed to handle 15 amps, that would be a 14 gauge wire. That determines what the thickness of the wire is. If it were a 20 amp circuit, by code, it would have to be a 12 gauge wire. And these are just, convenient things to know, that if you ever happen to be building circuitry, then you'll see that, oh, okay, I have to meet certain codes, and this is how you meet codes. It's determined by the gauge of the wire. The lower the number, the fatter the wire, the lower the resistance, the less heat it generates. Okay. Now what we're going to do really quickly before we take another break is start another wipe. Why does it keep saying that? I don't want to make comments. Okay. So we're going to draw a battery. A battery has a plus and a minus terminal. Now we're going to draw another thing that has a this in it. What does that look like, everybody?
That looks like a sine wave.
Looks like a sine wave. Okay. So if I were to draw a circuit that had a battery in it like this and put a resistor on it, which way does the current flow? It flows from plus to minus. If I were to do the same thing with a sine wave makes a voltage that goes plus and minus, but it alternates. It goes plus and minus and plus and minus. So that is alternating current. This is known as DC up top. It's direct current, always in the same direction. On the bottom is known as alternating current. It changes direction continuously, one to the other, to the other, to the other. So what that means is when it's on the positive side, which we'll use green for, the current will flow this way because the positive terminal is over here and the negative terminal is over here. But then at the other part of the cycle, which we're down here, the positive terminal is here and the negative terminal is here, so the current flows this way. Which means that your current through your resistor will flow, it will flow this way. And then the other half of the cycle, it will flow this way. So that actually means that we're using the same electrons over and over and over and over, and they're just going back and forth through the circuit. But does the resistor care which way the electrons are flowing? It does not. Therefore, it doesn't actually make a difference. Now, another thing that's important, which you're not going to be tested on, but it's important to know, is that you might actually be tested on. If I have 120 volts DC, then my voltage is this. That's my voltage, and it's at 120 volts, and it's all the time. Now, if I were to take a meter and stick this into my socket on my wall, I would probably want to be wearing gloves, but I would read that this is 120 volts AC. Now, if I were to take this and look at this on an oscilloscope, which is a device for measuring voltage versus time, I would actually see this. But what did we already say that the DC voltage was? We said that was 120 volts. Okay, so what gives? How come my AC voltage goes way above that and then way below? And in fact, if I were to measure it, it would be 170 volts and it would be negative 170 way down here. Anyone have any guesses as to why?
Is it pushing through the resistance?
Nope. Even if I disconnected it, even if I had no resistor whatsoever, and I measured my voltage, it would actually look like this. It would peak at plus 170 and drop down to a negative peak of negative 170. But it's colloquially called 120 volts. This is your wall voltage. The reason being, somebody give me the power equation again. Ohm's law power equation. P is equal to what?
IE.
IE. I times E. It's the PIE equation. Okay. So now here's the question that I have for you. If I were to take the power right here when the voltage is 0, what is my power? What would my current be?
Zero.
It'd be nothing. That's right. I'd have no power. But now, how about when the voltage was really, really high at its peak, way up here? It would be at a peak, right? Okay. Now, how about when it was way down below? Resistors don't really care whether it's flowing one way or the other, do they? It's just movement of electrons. So what that actually means is that at this peak and at this peak, we are actually producing more power than the DC would make.
So is it sustained voltage then?
The DC is sustained, the AC is not.
Right.
Our power actually goes up. Our power looks actually like this.
Mhm.
The DC power would look like this. This is actually something called RMS, which is root mean square. And the reason that people do this is the reason that we actually use this is that RMS, because people want to know how much power can be made by a certain battery or by a certain voltage source. People essentially want AC power, which is what's in our wall, capable of making the same amount of power as a 120 volt battery. So over a period of time, that is the average amount of power made by that voltage. That is known as our RMS. So when we actually look to our 120 volts AC, this is the amount of AC, this is the equivalent amount of DC voltage that would make the same amount of power as an AC waveform. This is known as 120 volts RMS. But in order to make up for the fact that it goes through 0, and sometimes it's producing less, at its peak, it actually has to make more. So anyway, that's what's inside your wall. That's why if you go to measure it and look at it, it won't look exactly like what you think it's supposed to look like. That's also why some circuits will actually be designed with components that are capable of handling 200 volts, but it's a 120 volt circuit. Why would you need 200 volts? Why would you need something that can handle a 200 volt value? And the reason being that those voltages they actually get pretty big inside your wall, higher than people think. Everybody ready for a 10-minute break?
Yes.
Okay, I'm going to try without killing Zoom to figure out how to do this. So, but if anyone has any questions, by all means, keep asking.
If you kill it, we'll be back.
Okay, I appreciate that. But if anyone has any continued questions, now's a good time to ask. Because we're actually going to move into AC more in a minute. So I want to make sure that everybody's comfortable with alternating current versus direct current.
So just a question on the equations and the
Yeah.
test.
Uh-huh.
So if we memorize those three.
Yep.
We should be good.
If
So
you
far.
if you scribble
far.
them down, as soon as you get the paper, you are fine.
Oh, okay. All right. I got you.
Yeah, you can make
Area.
as many notes as you want on that blank sheet of paper as soon as the test starts. Call it a brain dump.
Oh, I see. That's okay. Yeah. So right as soon as the test starts and they check you out, whatever before the test,
Yes.
that you're clean and sanitary. You can
Yes.
write some quick notes from your brain.
Yep.
Okay.
Yep. And I actually used to do that in college. That was one of my things. I had to remember something just long enough to write it down.
Yeah. All right.
Yeah, no.
Go ahead.
So RMS is RMS like root mean square?
It is root mean squared. It's actually the integral of the square over an entire period. It's the
Entire period,
sorry,
okay.
it's the square it's the square root of the integral over an entire period of the function squared.
But in farmer English, it's just kind of the average.
It's an
of
equivalent
that
power
voltage across time.
Well, it's an it's the voltage that is capable of producing or delivering the same amount of power as a DC voltage.
Okay. Yeah,
Yeah,
I get it.
So
it's the area under the curve.
yes. Now, a sine wave will have a different RMS power and voltage than a triangle wave or a square wave because the curve is different. So if you've ever if you go to buy a meter like a voltmeter, one of the things that you will see is that there are some voltmeters that do not say true RMS reading and some voltmeters that say true RMS reading. The ones that say true RMS reading are a lot more expensive because they're actually doing calculations. They're not just measuring peaks and saying, we're going to take 70% of the peak and that's the value. So a true RMS reading voltmeter is much more expensive because it's actually doing math. Does that make sense?
Yeah, that makes sense.
I don't understand this. I have Whiteboard Classic clicked. So weird. Whiteboard by default, if available. Okay, let's see if that works. In order to switch back to Classic Whiteboard, unselect the by default and revert back to Classic Whiteboard in the next meeting. Okay, so it has been updated. Okay, now it probably won't work the rest of today, but it might work for tomorrow, and I'll certainly try it out. All right, other questions? Nothing? Nada? Let me try opening a whiteboard and see what it does. It's okay. It's going to be after I do a new one, I think. That's too bad. I don't want to collab. I like collaboration, but sometimes it's not appropriate. And you know what burns me? I really did check. Hey, Gary,
Yeah.
you still with me, Gary?
Yeah.
All right, you holding on okay?
Oh, yeah.
Okay.
No, this is great.
Wait till we get to antennas, everyone. Antennas are fun.
Antennas are real.
Antennas are the most fun that you can have in radio. Well, other than maybe operating. So,
Yeah. Can I ask you a question?
yes.
Yeah. On the test, we're not gonna have a test knowing what's the RMS voltage, like the peak voltage, like 0.70 or the average voltage,
If
and we
you
didn't need to know that, do we?
if
on
you
the
go to
test?
if you want to take the general exam, it's going to be on the general test. I can guarantee you.
Oh, the peak. Oh my God. Okay. Well, okay. So it's not gonna be on the base. Okay.
It won't be
I
on
was
the
wondering
technician
about
exam.
that.
It won't be on the
Okay.
technician exam, but it will.
Yeah.
I can guarantee it'll be on the general exam.
Okay. All right. That was just a question. I hope it wasn't crazy or a dumb question. I
Not
was
at
just
all.
going, I want to know what's going to be on the test.
Yeah.
Yeah.
Jessica's got her hand up. How
Oh,
polite.
thank you. Thank you.
Hey, I wanted to say that when I looked at the study guide, all of this looked like alien speak to me,
Uh-huh.
but you are making this make sense despite technical difficulties. So thank you so much. Because I am
appreciate it.
absolutely horrible at math, horrible at equations, and had my head in my hands all weekend trying to understand this. So thank you.
Okay, good. I appreciate that. That's one of the things that I really enjoy is the fact that 90% of electrical problems are really solved by Ohm's law 1 and 2. And like if you start to look at a let's say a 50-watt radio, all right? Okay, everybody in their head, 50 watts, battery is roughly 12 volts. How many amps would that be? So 50 divided by 12 is about 4. Right? There's a lot of things you can do just, kind of like in your head after a while. Now, one problem is that if you were to try to hook up that 50-watt radio to a 4 amp power supply, it would not work and it would just sort of shut down. The reason that would not work is because transistors and other devices that make power are not 100% efficient. And you have extra power that runs the equipment. So really, to run a 50-watt radio, you need about 120 watts of power available. So, all right, everybody ready?
Now, what part was you saying again that it was going to be on the general? Was you talking about the calculations or was it something else?
RMS calculation.
Okay.
And you may wonder, okay, well, what importance is there in RMS? There's actually a lot of importance in RMS because most of the time, most of what we do is not DC. There's a lot of DC, but if we're talking about RF, radio frequency, it's just a very high frequency sine wave. Well, sine waves are AC, and AC power is calculated with RMS. So that's one thing that's really important, figuring out what peak voltages are on a piece of coaxial cable so you don't punch a hole in it electrically, stuff like that. It's actually really important. So for those of you, and I hope most of you will consider going beyond the technician exam, because that's really where a lot of the fun happens, is in the general class and above. You get all kinds of privileges to operate on the air, to do all kinds of cool things. It actually gives you the chance to really see firsthand how a lot of these things work. I know at this point it's still kind of like, pie in the sky. Pie in the sky. I guess pie in the sky. Okay, so next thing we're going to draw.
Capacitor.
Okay, what's that thing on top? We saw that already once. That's a resistor.
Resistant.
Okay, the thing below it.
Capacitor.
Yep, that's a capacitor. And the thing below that?
Inductor.
That's an inductor. Okay.
Conductor.
Now, so if a resistor is just a linear thing. If I put a voltage in, I get a proportional current through it. And what is Ohm's law? I'm going to keep quizzing you guys on this. Ohm's law again?
E equals IR.
E equals I times R. Exactly. And you can draw it like this, and E equals I times R. There's our circle. Some people draw it as a triangle. I don't care how you draw it, just so long as you do it and you remember it. Okay. Now, does Ohm's law apply to capacitors? Sure. This is a capacitor, letter C. We measure that in a unit of F, which is short for farads, named after Michael Faraday. We also have this thing called an inductor, measured in letter H for henries, named after Henry. Who knew? And so these are devices that, now, what we say about a resistor, power in equals power out. A capacitor is a device that can store energy in an electric field. An inductor is a device that can store energy in a magnetic field, or sometimes we write it with the letter H. Sometimes we write that with the letter B. But at any rate, it stores energy in a magnetic field. So power in does not immediately turn into power out. What we're going to do to show you this is we're going to make a capacitor. A capacitor is made of two big metal plates. And what we're going to do is hook this up to a source of electrons. Well, the electrons are going to balance out. We're going to end up with a whole bunch of electrons over here. And due to electrostatics, what do you think is going to happen to any electrons that are floating around on this plate here? What happens if I put a negative charge here and a negative charge here? What will these things do to each other?
Repel.
They will repel. They will try to get apart. Like charges repel. Just like when you put two North Pole magnets together, they will try to repel. If you have two static charges that are the same, your electrons, now in this case, will go this way, and the electrons will go this way, and you'll end up with positive charges over here. So here's our pluses, and here's our minuses. Now, in this case, pluses just mean it's a lack of electrons. But now, what do we have? We have a plus and a minus, and they're separated by a distance. What are they going to try to do? Opposites do what?
Attract.
Opposites attract. Those charges are now going to attempt to take these big metal plates and pull them together. They're going to actually try to pull them together. And if they have enough voltage, they will actually jump across that gap. But if they don't have enough voltage, they will just continue to pull. That act of pulling generates a force. That force is in the form of something called a field. The strength of the field is determined by the voltages that are over here. This would be a V minus, and this would be a V plus. And by the material, whatever that happens to be, inside here. So that could be air. Air typically doesn't conduct electricity. That could be mica. which is a form of rock. That could be polyethylene. It could be polystyrene. Those are plastics. It could be glass. It could be plastic, other forms of plastic, any number of different things. These are known as dielectrics. And a dielectric is something that is a material that does not conduct electricity well. A conductor is something that does conduct electricity well. An insulator is something that doesn't. A dielectric is a form of something that doesn't conduct electricity well. So what you have now is, let's say that I have taken a minus over here and a plus over here, and I hook these up and I let nature take its course, and this gap can't be closed. And now I have pluses and minuses formed over here. And guess what? What happens if I take this and I get rid of this? What happens to those charges?
Balance.
How? How do they balance? There's
They
nowhere for them to
dissipate?
go. No, they just sit there. So if I charge up a capacitor and I leave it, so let's say I hook it up to the minus and the plus over here, and I leave it connected and then disconnect these wires, my capacitor is charged. It doesn't, those charges don't have anywhere to go. My energy is now stored in an electric field because those charges are unbalanced. How about if I were to take this and hook this up through a resistor? Now what would happen?
Would flow through that
It'd flow through
resistor.
the resistor and we would be uncharged again. The charges would now go away and we'd be all neutral and everything would go back to normal. All right. That's actually known as a bleeder resistor. On a large capacitor, that is how you, if you don't want a charge there, you put a bleeder resistor across it and the capacitor becomes uncharged. Now, let's take a look at this. We're going to hook this up to minus and we're going to hook it up to plus. This becomes now minus, 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 minus. There's an extra amount of pluses over here. And now we are going to pull this battery off. I'm going to disconnect it. But we're going to do something here. Now we're going to make the positive up top. And now we're going to make the negative down below. So what happens now? What happens to the minus charges that are there? They flow up to the positive. And what happens to the positives? They flow to the minus. And we go through a period of neutrality where all this disappears, right? Where there are no charges anymore. And eventually, sorry, what will happen? This is plus and this is minus. Eventually now this will become the positive terminal. And this will become the minus terminal. And now what happens if we flip this the other way? And we make this the minus terminal and this the positive terminal. These will flow toward the minus. These flow toward the minus. These flow toward the plus. And these flow toward the plus. And we end up with a period where we are neutral again, right? These go away. This goes away. These arrows go away. And this goes away. And now, eventually, we charge up to plus down here and minus up here. What's it called when we switch from plus to minus and plus to minus? What is that called?
Current.
That is called alternating current. Yeah, okay. So we're now switching from one to the other, back and forth and back and forth and back and forth. As far as the battery knows, if the battery did not know what was in this black box, and a battery can't possibly know what's inside a black box, right? All it knows is that it seems like whenever the current switches back and forth, when the voltage switches back and forth, you get current flow. What does that look like? If you know that it seems to carry current, that has a name. If something seems to carry current all the time, what is that? What is that? What is that, everyone?
A wire.
That is a wire. So if you have AC connected to a capacitor, it does a magic trick. What is the magic trick? The magic trick is that the AC flows right through the capacitor by virtue of inducing electric fields and moving currents moving electrons from one side to the other. That's what AC does when it hits a capacitor. What happens when DC hits a capacitor?
Stores it.
It just stores it up. Oops. It just stores it as energy. So that charges up, and then it looks like an open circuit. AC, it looks like a short circuit. So now we're going to take an inductor instead of a capacitor. An inductor is a coil of wire. If we create a current flowing on a coil of wire, so here's our current I, this will make a magnetic field that forms in rings around the wire. When it gets to the coil, it will actually make magnetic field lines that go like this. If anyone has ever built an electromagnet with a nail and a piece of wire and used it to pick up paper clips, this is exactly what that's doing. So what happens is your current creates a magnetic field, which you can then use. So in an inductor, a current generates a magnetic field. Energy is then stored in the magnetic field. Now, unfortunately, what ends up happening here is that if a capacitor is left charged and disconnected, what happens? It just sits there. If an inductor is left with a magnetic field floating around like this, in space, you have energy that is now floating around in space. There is nowhere for that magnetic field energy to go. Once it's disconnected. So what will happen is the energy will generate a voltage that attempts to allow a current to then be initiated. And what will happen is you will have all this magnetic field energy that now has to go somewhere, and it generates a big positive voltage and a big negative voltage in an attempt to create a current flow to get rid of the energy. Because you can't have energy that's just sitting in space. Doesn't work. So it works with a capacitor, but not with an inductor. So what is it called when you generate, let's say, 50,000 volts over here? And you have 0 volts over here. What will happen if you have 50,000 volts on one side and no volts on the other side? That's a lot of voltage. That will make something. What's that called?
Arc.
That will make a spark. Yes.
Like a
This
Tesla coil.
That is just like a coil. That is exactly how old school ignition systems worked. You would initiate a current in a coil of wire, and then you would suddenly break it and give it nowhere to go, which would then create a very large spark, which would then be used to light off a spark plug.
Scott?
Yeah.
I took my son, he must have been in high school, down to LA, and we went to the observatory there, and he saw a major Tesla coil. That inspired him to go to OIT and become an engineer.
That's cool. Yep. If anyone's ever seen a Jacob's ladder, that's how you initiate a Jacob's ladder. You create a very large voltage and give the energy nowhere to go. Give the magnetic field energy nowhere to go. It has to go somewhere. So now, if I have a DC coil, right? If I have a coil that is carrying DC, here's an inductor. It's carrying DC and it makes a magnetic field and it's always going the same direction. The inductor is very happy. It is just a piece of wire with a static magnetic field. But now let's say that I tell the inductor, hey, you know what? I am going to allow you to have a magnetic field that formed, but then I'm going to reverse it. So it was going this way, but now I switched it and now we're going this way. So your magnetic field that was going this way, now, no, I want you to go this way instead. Magnetic fields don't like to be changed. So if I put AC into a coil, what will happen is it will act like an open circuit. If I put DC into a coil in the extreme, it will act like a short circuit. So here's the capacitor, and here's the inductor. And notice that in the extreme, they act completely separate. They act completely opposite of each other, do they not? And that's just because of the physics of the device itself. So now, here's what gets really cool. And I say really cool because I think it's really cool. Let's say that I have a voltage that looks like this. Here's my weird looking voltage. All right, everybody, what is this called? It's a little pointy, but what is that called?
It's a sine wave.
Sine wave. Is that AC or DC?
AC.
AC. Okay. Now, if I were a little bit tricky, could I take this sine wave and give it a bias so that it looked like this, that it was always plus? Could I do that?
I imagine so.
Yeah. You know what you do? You do this. You put a battery here.
You can. And
here's AC. And you run them in series. And now you have a biased sine wave. So you have a sine wave with a DC bias, which gives it that.
Mm-hmm.
Okay, so now I have this kind of funky looking wave, which is a sine wave with a bias voltage on it, a DC bias. Okay, so now let us say that I built a circuit that looked like this. And this wave form, that voltage was entered into it. What would I get? Here and here.
You get a switch, right?
What you get at that point is that because there's actually an AC component and a DC component on that side, on that wave, you would actually get the AC over here and you would get the DC over here. It would split them.
Mm-hmm.
If I were to draw it like this, wow, that was terrible. If I were to draw it like that, I would get AC coming through here and the DC would come down through here. So you can actually use these components, which are very different than resistors, to separate AC and DC. This is what is used in amplifiers. We use this kind of thing all the time. This is a foundational portion of electronics. The fact that those devices behave in that way allows us to do all kinds of cool stuff. It allows us to separate AC and DC. Okay, so now we're going to add something to this. Anyone know what this is called? Anyone?
Dial.
That's a diode.
diode.
Okay. That is a diode. A diode consists of a semiconductor material. Now, we said a conductor is something that conducts electricity, right? An insulator is something that does not. A semiconductor is something kind of in between. Usually this is made of silicon or germanium, which they typically have 4 electrons in their outer shell. So they're kind of conductors and they're kind of not. So we have this intrinsic block of silicon right here, which if you try to put electrons into it, maybe they flow and maybe they don't. Not so great. However, if you were to do something with this silicon and add a couple of minuses, or you were to take this silicon and add a few pluses inside, that would change how it behaved, because there'd be a few extra electrons or a few electrons missing from those little blocks. By taking these and butting them up against each other, we have a P and we have an N. That would actually cause electrons to, if they got pushed in here, they would eventually make it at some point past this point and be attracted to this material. And since we know the current flows this way, what we end up with is current that only flows in one direction. That is the hallmark of a diode. If we put a small voltage over here, we are able to overcome the properties of the material, which we have basically doped the silicon by adding a few extra elements to it, either phosphorus or something to the boron.
What happens if you didn't have a diode?
Wouldn't work.
And what ends up happening is if we put a voltage across at, let's say, 0.7 volts, plus and minus, that is enough to cause this diode to conduct in the forward direction. If we do not have at least that voltage, this channel is then blocked. This is a one-way street. This is for silicon. If it's germanium, it's about 0.3 volts. And that's known as a forward bias voltage. So this is a 2-terminal device that basically functions as a one-way street. Now, when would one-way streets be necessary? Why would we ever want this? The reason that we would want this is because, let's say that we have something that looks like this. What kind of voltage is that, everyone?
AC.
AC. Okay. What happens if we take this
AC.
we do this with it? If we put this into here, what happens on the other side?
Direct current?
Yeah, what does it look like? If we have this to start, what does it look like on the other side? Whenever it goes positive, it conducts. Well, it goes through some flat lines, right? But what happens there? Does it ever go negative?
No.
No, it doesn't.
No,
So
well,
now
it changed from AC to DC then,
that's right. Now this is what we
right?
call ugly DC. I don't think that's a technical term, but that's what I would call it. That's very ugly DC. It has a lot of what's known as ripple. So can you think of something that would charge up at a certain voltage with DC and then be able to give back the charge that it has stored?
A light bulb?
Your capacitors?
How about a capacitor? Yeah, so the capacitor charges up right here.
Yeah.
And then
Because
when
what it does is it gives you your continuous feed
right,
of DC.
so what happens is the capacitor charges up, and when the voltage coming in goes down, the capacitor starts to discharge, and then it continues to do this. So now the DC is not quite as ugly. Now we could do a bigger capacitor that would make it smoother. We could also, at that point, do something that looks like this. This is a special diode that is called a Zener diode, which is designed to run backwards. And I'm actually going to add a resistor here just to be safe. I don't want to blow it up. And we can add a small resistance over here if we really want to. And this is a reference voltage diode. Above a certain voltage, it will allow something to flow in the reverse direction. So that's a special kind of diode called a Zener diode. And let's say this was a 5-volt Zener diode. And this was, let's say, 16 volts AC. Well, okay, so anything above 5 volts, we allow it to open up, and now we end up with this being flat topped right there at 5 volts. So we have now taken AC, and what have we made out of it? Does anyone see an application for this? Anybody?
A rotostat?
Does anyone see it?
A rotostat, like something that you turn a knob?
Nah, you see them, you use them every day.
Step down or step up your power?
Yeah, but even more so. Can you think of anything that you use every single day that converts AC to 5 volts DC?
Your power supplies.
Power supply for a cell phone.
Yeah.
USB voltage. This is basically the diode is what gave us the ability to create a power supply that is compact. Now, we can go one step even further because this is somewhat limited. And we're going to add a device here. Okay, so here's our okay, so we go this way. And then we go out and we come back this way. Or we go this way. And we come back and we go back this way. And then we put a diode like this, and a diode like this, and a diode like this, and a diode like this. Has anybody ever? Nope, not yet. Has anyone ever seen one of these?
Yeah.
This is called a full wave. This is called a full wave bridge rectifier, and it takes AC, and instead of zeroing out, essentially it allows only one path, one complete circuit like this. Oops, wrong color. So when the voltage goes positive, for instance, the circuit goes like this. It follows the path, and we go all the way around. When the voltage goes the other way, we go like this.
Steve? or Scott.
Yeah.
We used to use these, it's Rich, we used to use these at NEC for our phone systems because there were always negative 48 volt DC.
Mm-hmm.
So we used to bring a rectifier and a strain of batteries.
Yep.
So even if the power was out, you would still have, phone service.
Mm-hmm. Well, the way that this works, this is a full wave bridge rectifier. What this does, remember what we saw with the diode, that it trimmed off half of the voltage? This does this. A lot more efficient. So this is what is actually typically used. It takes 4 diodes, but you get a much more efficient voltage waveform instead of this. A lot more power. Then the next thing to do with it is, okay, what we're going to do is we're going to take 2 diodes and we're going to stick them back to back. This is P and this is N and this is P type, or we can stack them and go NPN. And then we put a terminal here and a terminal here and a terminal here. This is a 3-terminal device instead of 2. A diode is 2 terminals, right? But this is 3 terminals. It's got 3 wires hooked up to it. But if you were to look at this, you would see that this is just, we're going to go with a P with this one right here.
What does the P and N stand for?
That's the type of silicon. So
Okay,
remember, so you've got either P silicon or N silicon, depending on the doping agent that has been added to it, to either give it a few extra holes, which are a lack of electrons, or a few extra electrons. And that basically tilts it one way or the other. And that gives you the ability to have a one-way street. Okay, so now this is now a stack of 3 things. Well, in here, you still have this PN. And what happens is you push into there. Actually, I think I did that. No, that's right. Okay, so you can put a current into here by putting a voltage there. That makes a small current flow. What ends up happening is that amount of voltage essentially turns on this back channel, which is a whole NPN. And if you put a voltage over here, you will get a gigantic cascade of current down here. So a small current over here makes a really big current over here. Well, what do we know about power and voltage and current? What's Ohm's law, everybody?
E equals IR.
And what's the other one?
Power
E equals I over
Power
R.
times
Other
power
one's
times
pi.
I times V.
Yep, P equals I times E. Okay, so if we have a lot of current and a lot of voltage, we get a lot of power. So a small amount of voltage and current and power generates a big amount of voltage and current and power, allowing it to flow. And it's proportional. So if I have something that looks like this over here in time, over here, I might have something that looks like this. What is that called?
Step up.
It has another name.
Amplified.
Amplification. You're making a bigger copy of something. This is an amplifier. A transistor is a basis. This is known as a transistor. This is the basis for amplification. The amount of gain that you get is known as the beta of the transistor, which you don't have to remember. But this can be on the order of 100, 200 times. So if I have 1 milliamp over here, I might have 200 milliamps of current over here. And it is proportional, which means if I have a tiny signal over here, I can get a huge signal on the other side. If I've designed my amplifier correctly, I can get a really, really nice copy of it. So where do you find applications for this?
Volume?
Volume control. Yep. Where else? If you want to listen to a cell phone.
Signal boosting?
Yeah. I mean, if you have a speaker. I mean, you take
stereo.
Like a stereo. Yeah. And the cleaner your amplification is, the more truly you'll replicate your sound. And that is that is the primary, or one of the primary uses of a transistor. Now, there are a couple of different kinds of transistors to talk about. One of which is, it looks like this as we draw it. This is actually a representation of an NPN transistor. This is known as a bipolar junction transistor, or BJT. It has 3 terminals. These are known as the collector, the base, and the emitter. And this is where the bias current goes from the base to the emitter. And you have a cascading amount of current flowing from the collector to the emitter. That's proportional to the base to emitter current. There's another form of transistor, which we can draw, and it may actually have something in it that you recognize. Just from this morning. What do you see right in the middle of it?
Capacitor?
A capacitor. Okay. So if I put a voltage over here, what does a capacitor do? How does it store energy?
In an electrical field?
Electric field. So if I put minuses over here, what will happen over here? I'll have pluses attracted to it. Depending on the voltage that I put right here on this side, this is known as the gate, or G. That will determine what my channel looks like as far as being able to carry current.
Hey, Scott.
Yes.
Are a lot of what you're drawing in the materials folder and the symbols used in circuit diagrams?
Yep. So this is known as a FET, or field effect transistor. Any guess why it's called a field effect transistor?
Because of how it stores the energy?
Well, not that it has stored energy, but how does a capacitor work?
It stores it in the electrical field.
Electric field, that's right. So it basically operates on the electric field. So this is a field effect transistor. And it has 3 terminals, except that they are the gate, the drain, and the source. And what's important to note is that a bipolar junction transistor operates on current, and this operates on voltage. The end effect is very similar. They both allow a very large, proportional current to flow. But this operates on a voltage at the gate as opposed to a current. So which one do you think is more efficient?
FPT, I think.
A FET. And why is a FET more efficient? Because this one actually uses current. What is a voltage? How much current flows if this is an open circuit? How much current flows if that's an open circuit?
None?
None. That's right. So a FET is extremely efficient. And in fact, most small modern technology uses FETs. This is the basis for what's inside every microprocessor because it's so much more efficient. If we were to build an iPhone, for instance, with bipolar junction transistors, if you could make them small enough, it would get very, very hot. Extremely hot. Because there's a lot of power being dissipated. Okay. So we've kind of talked about transistors. And I am just looking through the book, and one thing we haven't covered yet is decibels and gain, which we're going to do. There's resistors, transistors, inductors, batteries. Okay. So batteries. There are two kinds of batteries. And by the way, if anyone is curious, we're roughly on page 23 of the book. And I do actually follow the book more closely as we go further into the material, because it basically is just more applicable to follow the book.
When you say the book, what book are you talking about?
Do you have the book?
I might not, unless it's a study guide.
It's the study guide.
Okay, I do have it. I've been going through it. Yep.
Okay. So for instance, what you may find is that, let's say we are on this page, which is page 29. There's our single diode, number 5. There's our Zener diode at number 10. Now, one thing that is interesting about the exam is that notice that it asks about number 4, right? Well, number 4 is actually numbered. What is number 4?
Capacitor.
That is not a capacitor.
Transformer.
That is a transformer. So even though it doesn't list it, I find it important to discuss what a transformer is, because it's another one of these really important foundational devices that we use every day. And so we're going to draw a transformer right now. Uh-oh, what's that? Everybody, what is that?
Inductor.
That's an inductor. Okay. What does an inductor make around it when it's carrying current?
Magnetic field.
A magnetic field. Okay. Now, what if I draw another inductor over here? And some of these magnetic field lines extend out to here. What will happen in that other inductor? It will pick up some of those magnetic field lines, and what will happen inside it?
Make it
Charge
current?
them.
Well, if I have a current over here making a magnetic field, the
Would
magnetic...
it make it?
Go ahead.
Would it make it attracted?
Nope.
It moves the electrons in the other wire.
It moves the electrons in the other wire and makes a current. This is mutual inductance. And what ends up happening here is that if I can, instead of doing these magnetic field lines, let's say that I have a material that goes like this. And I make it square so that it passes right through the middle of both of those inductors, and it happens to be made of something like iron, which is it creates a good path for magnetic fields to follow. That magnetic field, instead of just flowing through the air, is really concentrated in that material. What ends up happening now is if I create a magnetic field, it gets concentrated inside that material, which is very often iron or steel, because steel has a lot of iron. It's known as a ferromagnetic material. The magnetic field is constrained inside the material. So if I can get 95% of the magnetic field inside here, what will happen on the other side? I will get a ton of magnetic field on the other side. Well, if I get a ton of magnetic field on the other side, what will happen to the current? If I have current going in, I get a lot of current going out. So the benefit of doing this is that these are now isolated from each other, aren't they? These two sides are actually not connected. They are coupled together by a magnetic field. But the wires are not physically connected, are they?
Right.
Nope. It's just coupled together by a magnetic field. So an interesting property of a transformer is that the amount of flux, as it's called, magnetic flux, that is made is proportional to the number of turns of wire that is wrapped around it. So now, if I instead draw this core, but instead of that, I now have, let's say, this. A whole bunch of turns of wire. And now I draw the core. I still have current flowing, but let's say that I have a ratio of 10 to 1. So I have, let's say, 100 turns of wire wrapped around this side and only 10 turns of wire wrapped around this side. If I put 120 volts on this side, I will get 12 volts on this side. And transformers only work with AC. They don't work with DC. But what I get is a turn down. Now, I could actually make the ratio opposite, in which case, let's say I had a 1 to 10 ratio. If I put 12 volts, 120 volts in over here, I would get 1,200 volts over here. Can anyone think of any applications for that? For either one?
Power poles.
Power poles, yes. Because your power lines are roughly at 12,000 volts. I don't want that in my house.
They're
So,
440, and then you
that's
have to
right.
step down to
Yeah, there's either 12,400, 13,800, and you have to step that down to either 480 or 240 or 120. So,
single phase or dual phase.
or three phase.
Three phase.
I use three phase at work all the time. So that allows you to change your voltage. And again, it doesn't change the frequency. The frequency in our wall voltage is 60 hertz. And that does not change. However, what does change is the voltages. So if that happens, let's say I have a ratio instead of 100 to 1, and I have 12 kV over here, I will get 120 volts over here. So what's the advantage of doing this? Somebody take a guess. What's the advantage of doing this? And I'll give you a hint. It comes down to Ohm's law.
It maintains your power level coming into it.
That's right. Okay, so let's say that my user on this end was using, oh, I don't know, 1,200 watts. Okay, so by Ohm's law, P equals I times E. Okay, so if I have 1,200 watts and 120 volts, what is my current?
.1 amp.
1,200 is equal to something times 120. Ten amps. Okay, so I'm using 10 amps of current on that side. Now, what is my power? I already said it's 1,200 watts. Transformers are pretty efficient, like 98% efficient. So what we're going to do is go through our calculation again and look at our transformer. Say this is 12,000 volts. P equals I times E all over again. How much power are we using? That does not change.
1200 watts.
1200 watts. How much voltage? 12,000 volt. My current is?
We don't know.
Yeah, we do. Well, we do now.
Yeah.
It's 1/10 of an amp.
Yep.
Okay, so why is this important?
Measuring the circuit breaker.
Could be. But why is it really important? Let's say I have a power line. And my power line is hanging in the air between two poles. It has a resistance. What is my voltage? If I have a certain amount of current, how much voltage do I get over through it? What's Ohm's law?
E equals I over R.
E equals I times R.
Times R.
And let's say that this is 1 ohm. So for my high voltage side over here equals 1/10 times 1 ohm is 1/10 of a volt. How about on the other side? Let's say that I did it on the at 120 volts. I would have 10 amps times 1 ohm is 10 volts. What is my voltage on the right-hand side in the first place? 120 volts. How much voltage did I just waste in my power line? I just wasted 10 volts. In addition to that, I just burned that up as heat because of the resistance. On the other side, I had 12,000 volts and I just lost 1/10 of a volt. And because my current was so low, I burned up almost nothing in the form of heat. And that's why power companies use transformers. That's why they deliver power at really high voltages, because ohmic losses are calculated as a result of current. The more current they have to deliver, the greater the losses, the more their lines heat up, the bigger their power lines have to be. The higher the voltage they can deliver it at, the better off it is for everybody. And it all comes down to transformers. So now I'm going to draw a transformer again. Here's our transformer. And I'm going to have, let's say, a 3-to-1 ratio. And if I have a voltage over here, I will have 1/3 of that on this side because I have a 3-to-1 ratio. But because my power is constant, my power is equal to my power. And what's my formula for power? Everybody?
P equals I times E.
P equals I times E. And P equals I times E. So what happens to my resistance? Or what happens to my current if the power is constant and my voltage goes down by a factor of 3, my current must go up by a factor of 3. Okay. Now, what is my formula for Ohm's law? E equals I times
R.
R. Okay, we're back to that again. Okay, E equals I times R. We're going to arrange it for R. R is equal to E divided by I.
I.
Okay. And in this case, it's 1/3 divided by 3. And this is 1/3 V divided by I is equal to 1/9 V over I. Okay, that's my R. How about over here? Just V over I or E over I. So what that means is my resistance over here is 1/9 what it is over here. Well, that 1/9 is the square of that number 3, isn't it? And it turns out that I can actually take my impedance, as it's called, and convert that by the square of the turns ratio, because the voltage and current act opposite. One goes up, the other one goes down. Therefore, when I look at what happens, I can actually use this to change my impedance. Okay, so the next thing we're going to do, and I know we're almost done. So we're going to say that we have this thing called R. And what is R again, everyone?
Resistance.
Measured in
ohms.
Ohms. Okay. Well, we also have this thing called Z, which is impedance, which is also measured in ohms. That's a little confusing, isn't it? Why would they use ohms for the same for both? And the answer is I can't tell you exactly why, other than the fact that they are related. R is resistance. That is the ability of something to resist the flow of specifically DC current. Impedance, notice to impede, to resist, they're kind of similar words, right? This is the ability of something to resist the flow of AC. Exactly. Now, for a resistor, does it make a difference?
No.
Nope. For a resistor, resistance is equal to impedance. But now, just to make things interesting, we're going to do a capacitor. And remember what we saw for a capacitor. What happens if you push AC into a capacitor? It
goes straight through.
Goes right through. If something goes right through, does that mean it has high impedance or low impedance? Low impedance. So for a capacitor, this is very low impedance for AC. How about for an inductor? You try to push AC through it, and it blocks. So if it blocks it, what does it do? It has high impedance. And in fact, not only are they high or low, but if you're ready for this, this is where it gets a little interesting. And this is on the general class exam as well. And this is why this stuff is so interesting. Okay, so we're going to draw another XY plane. And we're going to say that this is our resistance over here. Can you ever have negative resistance in the practical world? No. So we're just going to cross out the negative sign. Okay. So you're going to have positive resistance. Now, what's interesting here is that there is something called reactance, which is a measure of how something behaves in response to alternating current. A capacitor goes this way. Well, given our usual way of thinking about things, is that plus or minus? Minus. Given, and an inductor goes this way. Okay. So that's positive, right? Well, okay.
Right.
so far, I guess we can sort of accept that a capacitor will accept AC to flow, and an inductor kind of impedes it, and it doesn't allow it to flow. So, okay, I guess we're okay with that. Now, what gets really weird is that not only are those true, but a capacitor's impedance or a capacitor's reactance is actually equal to 2 pi FL. Oh, that value, what is that little letter F that we did early this morning?
Frequency.
Frequency. It actually changes. So an inductor actually changes value depending on frequency. And a capacitor does also. Notice that little letter F down there?
Yeah, frequency.
So as the frequency changes, the capacitor and then the inductor behave differently, which is kind of messed up. But now this actually has some very interesting benefits because, as it turns out, we can use vector math and say that if our inductance is up here, for instance, our impedance is there and our resistance is here, the actual result is that big. They're actually perpendicular to each other. So if I have 3 ohms here and 4 ohms here, does everyone remember Pythagoras' theorem?
Mm-hmm.
A squared
3
plus b
times, 4
squared
times.
equals c.
That's actually 5.
Yeah.
So 3 and 4 added, they don't add together. They actually give you 5 ohms impedance. You don't have to remember this now, but if you go any further, you will have to know this. And the reason that it's so important is because of that letter F. That actually allows you to pick a letter L, which is inductance, and pick a letter C. And if you want to set them so that you have this and that, and they cancel each other, then you have to set them equal to each other. All right, so then what you end up with is this. Here we go. You set them equal and opposite. 2 pi FL equals 1 over 2 pi FC. And you solve for the frequency, and you get 1 over 2 pi square root of LC. This actually has a name. Has anyone seen this before?
No.
Yes.
Yes. What is it?
It's the, what do you mean, like the name of the equation?
Yeah. What is this? See that letter R? That is resonance.
It's the impedance.
This is
Oh,
resonance
frequency. Yeah,
This is the this is the resonant frequency at which the capacitor and the inductor completely cancel each other out. And why is this important? This is important because let's say that we want to be listening to one particular frequency, and we're listening to a whole bunch of people talking, and and in the frequency spectrum, they look like this. We hear a whole bunch of people talking. We hear a whole bunch of voices, but we only want to hear everything in this range, right here. My wife says I have selective hearing. Anyone else have that? Anyone else suffer from selective hearing? So you only listen to what you want to listen to? Okay. Well, sometimes we want to be able to do that. So we only want to listen to what's inside this little band. What can we do? Well, we can try to build something to filter out everything outside, which essentially eliminates all this stuff on the outside so that we don't hear it. Well, we need something that will respond specifically for this range of frequencies.
Is that a bandpass filter?
That is a bandpass filter. And the way that you build a bandpass filter is that you, sorry, I keep deleting these things, but I have to. Okay. The way that you build a bandpass filter, a very simple one, is we are going to do this just because we need a resistor of some kind, a little resistor. We'll call it like 0.1 ohms or something. And for all intents and purposes, you know what? Let's get rid of it because we don't really want it. Ideally, we want it small. And what's that, everyone?
Capacitor.
Capacitor.
I mean inductor.
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 And what's that?
That's a capacitor.
Okay. So we're going to talk about series, things that are in series, their resistances add together. Their impedances, which are letter Z, they add together. So if I had a resistor here, and I had R1 and R2, things that would be
R1
that would be R1 plus R2. Well, if I have ZL and ZC, but I know that this one is positive and this one is negative, and they're frequency dependent based on F is equal to 1 over 2 pi L square root of LC, could I pick my values of L and C so that my frequency was right where I wanted it? And at that point, these would be exactly equal and opposite and would cancel each other out. Well, if I do that, then my bandpass filter looks like this. And I can listen to what I want to listen to. These are frequency dependent components that allow me to build filters and listen to the parts of the world that I want to listen to. This is a profound thing because it allows us, for instance, if anyone has ever listened to a three-way speaker, you know, you have a woofer and a mid-range and a tweeter. This allows us to actually build components because there's no reason to send this voice to a tweeter. Similarly, if there's really high-pitched stuff, there's no reason to send that to the subwoofer because it's not going to be able to do anything with it. It's not designed for it. This allows us to separate things. This allows us to build componentry out of electronics that allows us to take these frequencies and these frequencies and these frequencies and move them into different places and do things with them.
What's a simple practical example of what you're talking about?
Ooh,
Why?
Okay. The best one is I'm actually going to draw a three-way speaker system, right? So I've got in my car, here's my speaker. I've got a big one. I've got a mid-range, and I've got the tweeter, which can be a ribbon tweeter. And this responds to greater than 3 kilohertz. And this responds to 100 to 3000 hertz. And this responds to less than 100 hertz because of the physical size, you know? So if I were to take my music and run it through a series of filters where I basically could take, you know, I'd split it off 3 ways. I'd run this through a low pass filter and I'd send that to my woofer, and I'd run this through a bandpass filter and run that to here, and I'd have a high pass filter over here, run that to my tweeter, then I've made use of my music and amplified it properly. That is filtering. I mean, if I were to look at a frequency spectrum of my music, it would be from 0 to, let's say, 20 kilohertz. And
Okay, I get that. But what I don't understand is, as a radio operator, ham radio operator, where am I going to use this to do what?
Everywhere.
What's an example though?
Okay. So as a ham radio operator, let's say that let's say I build a transmitter, and I'm going to say that I have a bandwidth that I want to transmit, and it goes from 14 to 14.35 megahertz. That is the 20-meter band. I build an amplifier circuit based on a transistor, right? And I have a spectrum that has a lot of stuff that here's my primary signal that I want to send out, right? But I also have something here and something here because I can't control everything that comes out of my circuit. I'm combining frequencies, I'm mixing things. There's actually a device called a mixer. Maybe I have another frequency over here and another one over here. Which one did I want to transmit? Only that one. And in fact, there are requirements that everything outside of a band has to be at least 60 decibels below the desired frequency. Out of band transmissions have to be attenuated by a certain amount. In order to achieve this, I need this filter, because that filter will take everything outside and give it a poor path to follow and make it all disappear. Which means that essentially what I have done is eliminated my components, eliminated the frequency components outside the desired band. The same thing on receive. I don't want to listen to things I don't want to listen to. You know, if I'm listening.
So in other words,
yeah.
So in other words, you eliminate distortion.
No, you're eliminating frequencies. Period.
But isn't it band? But it's not like band. We're talking about eliminates certain distortion for you to get a better frequency, better voice.
No, it eliminates. Well, I mean, it could be, but I mean, you know, you're eliminating frequencies that you don't want, period. Let's say that I am listening to somebody talking, and this is their voice. This is on the frequency spectrum. So 0 to, let's say, 10,000 hertz. And somebody comes in right over here, and another one's way over here, and another one's over here. If I have too wide of a receiver that can't reject things, and this is the one that I want, what am I going to hear if I don't have that filtering available?
Okay.
I'm going to hear everything. I'm going to hear everyone. And it's going to be very hard to pick up the one that I do want. At that point, you would do something called bandpass filtering over right there, BPF, and that would eliminate those outside frequencies that you don't want.
Makes sense. I got it. Wow. I understand.
And all that comes from in an analog form. It can be done digitally, but all that in an analog form is done with capacitors and inductors. They are the basic componentry of frequency response or frequency dependent circuits. Okay, one more thing for today and then we're done. Okay, here we go. Series and parallel. Okay, this is parallel. Why is it parallel? Because current that flows this way has a choice of which way to go. It has two parallel paths. Series goes like this. Current has to go through both of them. What ends up happening in this case is that the current in a parallel circuit gets divided. Some of it goes this way, some of it goes that way. In a series circuit, which is at the bottom, your current has to go through both, which means that some of your voltage gets wasted in this resistor, and some of your voltage gets wasted in this resistor because of Ohm's law. E equals I times R. So on a series circuit, your resistances add. And in a parallel circuit, your R is actually less than either one. It's actually R1, R2 over R1 plus R2. So that being said, if I were to design a house, which way would I do my circuits? Like this, where those things are light bulbs? Which way would I want to design my circuit? On the left or on the right, if that's my house?
Left.
Left. Why is that?
Less resistant.
Oh, well, yes, but really, why is that?
Because if one bulb goes out, all of them don't go out.
That's right. And in fact, if they're not all identical, if you add another light bulb, it will actually change the brightness of each one on the right.
It'll act as a dimmer.
That's right. They'll all dim. This on the right-hand side, has anyone ever seen a circuit built like that? Christmas tree lights. Those are Christmas tree lights. That's why we don't build our house that way. Because on the left-hand side, we have our voltage, and here's our ground. Ground is our reference for 0 volts. Each of these devices, wherever they are, can be removed and not affect the other ones. Each of them also experiences the full supply voltage, which means that we actually get the proper amount of light or heat or whatever out of each one, independent of what's happening otherwise. This on the left-hand side, this is how we build our houses, thankfully. That's how I actually build electrical devices as well. On the right-hand side, this is actually quite rare. And that's it for today. And I will get the Zoom thing worked out by tomorrow. I have homework.
What page did you leave off in the book?
More or less, we've covered almost everything through page 34.
Okay.
We'll just clean up a few things up through page 34 tomorrow. And then we're going to get into more radio wave characteristics, propagation, antenna design, stuff like that.
Yeah. Can I ask you one question? No, I don't know if
Yes.
it's a dumb question.
No such thing.
When you talk about the bandwidth before you went to this one, and the impedance, does the tenor have something to do with it? How long or how short?
It does.
Oh,
if you
okay, that's what I was trying.
if you actually look at an antenna's frequency response, an antenna is a resonant device. That's why we build them the length that we build them. So if I were to, for instance, man, it's hard to draw a straight line. There we go. There's a good straight line. If I were to draw an antenna that looked like this.
Yes.
So this would be a half wave antenna at a given frequency, which would specify a certain wavelength. That antenna is going to have 0 current at either end, which means that my current distribution would basically look like this. And by the way, class is over, everybody. You can hang around or not. It's just question time. So basically, the current distribution is going to look like this on that antenna. The higher the current you have, the higher the field it generates. Now, the interesting thing is, if I were to try to stuff a different frequency onto here, the rules are the same. What is the rule when you get to the end of a piece of wire? Can you have any current? Yes or no?
No.
No, it can't exist. So if I were to draw this antenna and try to put a longer wavelength on it, I might only get this much current.
Oh.
If I were to put a smaller wavelength on it, I might actually get this. Which might actually work quite well. Maybe. So if I were to draw, so which one would it work best at, do you think? the very first one that I drew. Is so that would be a half wave antenna. Now, I could also play some tricks with this to put currents in phase with each other, and then you have an array factor. I could actually make it so that I had something like this, and then I had like a spacer that would absorb certain amount of energy, or allow me to space these things out so that I had like phasing sections that would allow me to put these currents in phase with each other at different frequencies. And then you basically pick a point and look in the distance and see if they're constructive or destructive, like way out here or out here, and see if these arrive at the same time. And if they arrive at the same time, then they're constructive, and then you have something called gain in that direction. We're going to get to gain tomorrow.
Oh, okay.
So there's now here's the other thing. Let's say that I had an antenna, and I'm going to draw that antenna one more time. If it lets me. Here we go. So here's the antenna. Okay. And I'm going to draw this wave. Yeah, okay, that's fine. This current distribution, and let's say that that's optimal, right? Then I pick a slightly different frequency, and it goes like this. A slightly different frequency, and it looks like this. A slightly different frequency, and it looks like this. This one right here is going to be the optimal frequency. If I were to plot all of those on a graph, I might find that as I go from 0 or, in a particular range, that the gain that I get, essentially how well the antenna works, might look like this. So if I have a signal coming in way over here, how well is that going to get through the antenna? If this is a map, or essentially a map in frequency of how well my antenna works at a given frequency. If I have a signal coming in over here on the left-hand side, how well is that going to work? You're muted.
Not too good.
Right. The same thing over here. If I'm way off frequency on the high side, how well is that antenna going to work? Essentially, it's behaving like a filter. If something comes in right in the middle, in that solid band where everything is good, it's going to behave better. It's going to transfer more energy to your receiver, essentially functioning as a filter. The tighter it is, let's say I build an antenna that has a really high Q, as it's called, really, really narrow banded. That would function as a really tight filter. And that actually has its place. I mean, we use them all the time. There's something called a magnetic loop, which has a really, really narrow bandwidth. And it's actually really good at rejecting signals outside of the desired band.
So it has a higher gain than on this?
No, not necessarily. It has a higher Q. It's a tighter bandwidth. If you look up Q factor, it's like a quality factor.
Okay, I gotta look at that.
And filters are measured by Q.
Okay.
So.
By Q. Okay, thank you for telling me that.
Yep. Other questions about anything? Let me go ahead and stop recording.
No.